Hello. In this lecture, as you can see, our focus is on one part of differential calculus which is called the expansion of functions. And as we go through the lecture, as we travel through the lecture, we will find that we are going to talk about the Taylor series and Maclaurin series for functions. Actually, they are expansions. And I will just start with the Taylor series and try to give a general flavor about what it tries to do. On the board, you can see a diagram. Evidently, this is the y-axis and this is the x-axis. Y-axis. This is the origin. Now we have the graph of some function y is equal to fx. It's an arbitrary function and a part of the graph has been shown. The focus is here. We have taken a point a comma 0. The value of x here is a. And there is another point. I would like to call it a neighboring point. In other words, h can be anything, but generally we take h close to, that means the value a plus h, the neighboring point is very close to a. And the question we ask ourselves is there any relationship that expresses f of a plus h in terms of f a h and perhaps some other terms that are related either to h or to a or to both. I repeat the question, or what we are searching for is, we ask ourselves, is there some way we can relate f a plus h, that means this ordinate, to f a, to h and to other terms. I have just written and written nothing, and other terms which are functions of a, h or both. That is the basic question, and the answer is yes, there is indeed a formula, and that is the Taylor series for expanding a function f a plus h in terms of f a in terms of h, and we will see once we write down the series what are the terms like. It is a very patterned series. It's not very difficult to remember. As we write down the series, we will come to observe those parts. So we rub out this and put up the series on board. Takes a bit of time just to rub the board. Yes, as I have said before, it's part of life. This is stated without a proof because we must have a working knowledge. So we are going to write the expansion for f a plus h, and here it goes. There is one assumption that we make, that the function fx is such that it is derivable infinitely. In other words, the successive derivatives for fx exist as many times as you please. If you want the 100th derivative, it's there. If you want the 75th derivative, it is there, and so on. But we need not go to so many terms. Now, the expansion goes as follows. F a plus h is equal to, first term is f a plus h f dash a plus h square by factorial 2 f double prime a plus h cubed by factorial 3 f triple prime a, and so on. And we go to the nth term, which of course is evidently going to be h to the power of n minus 1 factorial n minus 1 if n minus 1 times derived a plus after the nth term there will be something which we will call the remainder after n terms and denote that by r's of n. So, this r of n is called, I am writing this very explicitly, r of n is the remainder after n terms. It must be appreciated very clearly that once we come to this term h to the power of n minus 1 factorial n minus 1 if derived n minus 1 times and evaluated at a, this is the nth term, it is not the n minus 1th term. I repeat that this is the nth term, it is not the n minus 1th term. That is very evident from here. When I have one differentiation and h to the power of 1, this is the second term. When I have the third term, there are two differentiations. There is a square and there is a factorial 2. So, going like that and by logical reasoning, this happens to be the nth term. Hence, r's of n is the remainder after n terms. That is very significant. And following that pattern, r's of n is equal to h to the power of n if n a by factorial n. So, that is the remainder after n terms. It is very logically derivable from the way the terms are written down. Now, if we do one thing, if we assume that the remainder r's of n tends to 0 as n tends to infinity, that means if we assume, and in most cases this is true, that Rn tends to 0 as n tends to infinity, which in other words limit n tends to infinity r sub n is equal to 0, then this expansion can carry on till infinity. So, that is the series. Up to this we say it is in the finite form, and if we write in the following way, I will just write the infinite form. So, this is the finite form. Infinite form we write I will compact it to a sigma form. F a plus h is equal to sigma h, we put an r, let us say put an r by factorial r f r a r starting from 0 and r going to infinity. So, this will give us this particular series, and this is an infinite series. So, f a plus h is h to the power, the first term for example is r0, that means h to the power of 0 factorial 0 is 1, f not a means f a not differentiate. So, that is the first term. Second term is when r is 1, we have h to the power of 1 factorial 1, this is implied factorial 1, f single prime a, and so on. So, this is the Taylor's expansion in, I think, To my mind, this is the simplest way to write down the Taylor expansion. And now we will handle this Taylor series and get to the Maclaurin series, and that's 2 or 3 steps away from the Taylor series. Now, what we say about the Taylor series is, I will write it down, a part of the board. When we write the expanded form, that is the Taylor series. Gives us very simply the expansion, this is another way of saying it, about x is equal to a. This is another way of saying that the expansion, the Taylor series expansion for f a plus h gives us the expansion about the point x is equal to a. That can be any point, and the special case will arise when we take the expansion about the origin, that means about x is equal to 0. So, we will do that because actually in applications in mathematical physics and engineering problems, it is more important to be knowing the Maclaurin series than the Taylor series, and we just take 2 or 3 lines more to get down to the Maclaurin series from the Taylor series. So, we will do that. We will write down the expansion once again, and in 2 or 3 steps, we will arrive at the Maclaurin's series. Let's see. We put back the Taylor series once again. F a plus h is f a plus h f dash a h square factorial 2 f double dash a and so on. Now, if I take a is equal to 0, so I say let's choose a is equal to 0. That means instead of a being a floating point on the x-axis somewhere to the left of the origin, to the right of the origin, we peg it down to reside at the origin. In other words, we give a the value of 0. So, if we do that, we can write this becomes f 0 plus h is equal to f naught plus h f dash naught plus h square by factorial 2 f double dash naught h cubed by factorial 3 f 3 primes evaluated at 0 and so on to infinity, we say. Now, here this term is nothing but fh. 0 plus h is nothing but h. So, f h is expanded in terms of f naught, the value at the origin, f dash naught, the first derivative evaluated at the origin, and so on, so forth. Again, we get a pattern series. Here we would do one particular thing. We will replace this h, which is of course a variable, by the most general variable that we write for the independent variable. That means we replace every h by x. So this implies we will replace every h by x. Fx is equal to f naught plus x f dash naught plus x square by factorial 2 f double dash naught plus x cubed by factorial 3 f triple dash evaluated at origin, and so on to infinity. Ad infinitum, we say, ad infinitum. So this particular series, which gives fx as a power series, we will see very clearly that the powers of x successively increase. This is x to the power of 0, f naught x to the power of 0. This is x to the power of 1. The next term is x to the power of 2. The next term is x to the power of 3, and so on. So we call this Maclaurin series as a power series expansion for a function fx. So this last series, which I just put a star here, this star is called the Maclaurin's series. Maclaurin's series for fx. We will do a very simple example, because so far I think even in high school we've learned certain series. For example, we know the series for sin x, the series for cos x, the series for e to the power of x. We will derive these series one by one quickly, and then we will see that whatever we've learned in high school for the series expansion of certain known functions, which are elementary functions, of course we can get all of them one by one by using the Maclaurin's expansion. So I will put this right on top and see by a choice of different functions how to get the Maclaurin's expansion for certain well chosen functions. So give me a bit of time to rub the board. Thank you for that. So let us take as a very elementary example, expand e to the power of x as a power series in x. It's not necessary to put, but since we are doing this first time by using the Maclaurin's series expansion, Maclaurin's formula for series expansion. Now we have seen that we need the various derivatives of the function we are going to express in terms of Maclaurin series, power series in x. We need to evaluate the various derivatives, the first derivative, second derivative, third derivative, and nth derivative, and so on, evaluated at the origin. So we will do that first and then plug in the values we get into the formula for Maclaurin series. Now writing fx is equal to e to the power of x implies f dash x is e to the power of x, and this implies f dash 0 is 1. Also, this will be needed. F naught is e to the power of 0, that is 1. F double dash x is again e to the power of x, that implies f double dash 0 is 1. So, carrying on like this, we will see that all the derivatives of the function e to the power of x get a value of 1 for all values or all orders of differentiation. The nth derivative at x is equal to 0 if n prime 0 is also equal to 1. So, all the derivatives have value 1. If n naught is equal to 1 for all values of n. This is the compact way of writing it. Now, e to the power of x therefore is, this is the function, f naught is 1 plus x into f dash naught is 1 plus x square by factorial 2, f double dash naught is 1 plus x cube by factorial 3. Again, the third derivative at 0 is 1, and so on. The general term being x to the power of r factorial r into 1, and we write to infinity. So, this kind of series e to the power of x we have learnt earlier, 1 plus x square by factorial 2. In fact, whatever we get by doing the Maclaurin expansion is exactly what we expect. There is nothing, there is no deviation from our earlier knowledge. Just excuse me for a moment. Thank you. We now take another function. There is no harm in mentioning that e to the power of x, the function which is called the exponential function, can also be written as, and in many authors prefer to write always in this form, e x p bracket x is the same as e to the power of x. So, exponential is not expression, it is exponential function of x. Very simple. There are certain good properties which I don't want to digress, but one property I wish to mention is very simple, that e to the power of x for any value of x, positive, negative, 0, e to the power of x is always greater than 1, no matter what is the value of x. In other words, always greater than 0, or this means can never be negative. I have mentioned this point because, during my experience of teaching mathematics at various levels, in a hurry, you might find students drawing the graph, even if it's a sketch graph, of e to the power of x is something like this. This part is fake. This can never happen. E to the power of x can never be negative. It's a very important property. It's always greater than, can never be equal to 0. It's greater than 0, not equal to 0 at all. Our next example is to try and find the expansion for sin x by the Maclaurin's formula. So, example 2 we can write. Just write example. Write the power series for sin x. Note the wording of the problem. It can be explicit, it can be shrouded. In other words, here of course the message is write the Maclaurin series for sin x. And as I said before, the Maclaurin series is a power series in x. That means the series emerges in terms of the various powers of x. So for that we need first to evaluate the various derivatives of sin x and evaluate each of them at the origin, because that is ultimately the terms we need, the values we need once we plug the values in the expansion for sin x. So I will rub out this part and keep on generating the various values of sin x. Now here fx is sin x, f0 is 0, f dashed x is cos x, f dashed 0 is 1. F double dash x is minus sin x, f double dash 0 is 0. F triple dash x is minus cos x, f triple dash 0 is minus 1. And f derived 4 times x is sin x, and f derived 4 times at the origin is 0. Now it is very easy to see that we will get this set of values starting from here, not this value. Starting from here, if we keep on differentiating, we start at sine, then we get these values once again. So the next derivative will be cos x, and that will have a value of 1. So going by this process, we will see that after we apply the Maclaurin series, I will write it down because otherwise it might leave a little bit of confusion in the minds of some of the viewers. So first term is f naught. F naught is equal to 0. X f dash naught is x into 1. X into 1. X square by factorial 2 f double dash naught is x square by factorial 2, f double dash naught is 0. Next, x cubed by factorial 3, f triple dash naught is x cubed by factorial 3. Triple dash naught has a value of minus 1. So, minus 1. Get to the fourth term. X to the power of 4 factorial 4, f derived 4 times at the origin is x to the power of 4 factorial 4 into 0. So that is how it goes. Alternately, we get 1, 0, minus 1, 0. Again, the next cycle will be 1, 0, minus 1, 0. So, these are the various terms of the Maclaurin series. On the right of this, we will put down the series on the left and see what the series looks like. There are many ways of generating power series, but this happens to be a very convenient way. Now, by the formula for Maclaurin's series, we get sine of x, f0 is 0 plus x into 1, again 0 plus 0, x squared by 2, this is this term. So, the next term is x cubed by factorial 3 into minus 1, next term is 0 plus 0. Next term will be x to the power of 5 factorial 5 into plus 1. Now, one sees very clearly that there is no presence of any even powered term. In other words, what we've got so far is, if we just quickly simplify this, this is equal to x minus x cubed by factorial 3 plus x to the power of 5 by factorial 5 minus x to the power of 7 factorial 7 and so on. The readers can check all these value of derivatives after the third and fifth and so on, and they will of course come to this expansion that sin x is equal to this much. Now, is this expected? Let's see. Is this something expected? There is no square term. There is no x to the power of 4 term. We will say yes, this is indeed expected, because all of us know that sin x is an odd function. So, when we are expanding sin x as a power series in x, it is not expected that there will be a square term or a term of x to the power of 4 and so on. So, the observation is all terms are x to the power of 2n minus 1 type. In other words, x to the power of ODD. No term can have x to the power of even. Sin x is an odd function, and the definition of odd function is f minus x is minus of fx. Minus of fx. So, the sin x function falls into this category of odd functions, and therefore, it is perfect to expect this particular thing. Now, we will not remove this, we will use this once more for another small problem, and then we will go to the Maclaurin expansion for cos x.